I would like to show the magnetic field simulation using the Radia Python for multiple wiggler development. This is a multiple wiggler. The magnet along the electron beam will produce the high flux hard X-ray for the condensed matter experiment for synchrotron radiation facility. The magnetic array made of the magnet and the pole. The pole is the vanadium iron cobalt alloy to produce higher magnetic field rather than the magnet itself. Because of this soft material has higher permeability than the permanent magnet. The permanent magnet also higher magnetic field can be produced from neodymium iron boron magnet. Combination between the permanent magnet and the pole can be produced higher magnetic field for higher energy of X-ray for higher flux if the period of the magnet is higher or magnet itself is larger to produce higher magnetic field. The magnetic field between two magnetic arrays displayed in this picture can be vary between the gap between the magnet array upper and the bottom. The gap can be adjusted these two motors. The minimum gap can be calculated from each storage ring for the machine condition, emittance, and Betatron function. The smaller gap produces higher magnetic field, so smaller gap is better for the higher flux of higher energy and higher flux of the X-ray production. However, the electron beam passing through these two magnetic array gap passing through in the vacuum chamber to accelerate the electron nearly the light of the speed of the light. In that case, the magnet can be installed in the vacuum chamber. Then the magnetic field can be higher because we don't have to make a vacuum chamber between this gap between the magnetic array. This is the detailed magnetic configuration of the magnet of the one side of the array. Each pole surrounded by the magnet, permanent magnet. The small arrow indicates the magnetization direction. The pole has no magnetization. The magnetization of the pole depends on the magnet around. This picture shows 9 main poles, full poles, and the 2 end pole we call extremity. The magnet and pole align along with the electron beam and arrange correctly on the stable support structure. The magnetic field strength is plotted as a function of the gap between the magnetic array. The magnetic field is higher when the gap is smaller. When the gap is smaller, this is the 20 millimeter gap, 23 millimeter 3.27 3.5 mm gap flux density from the multiple wiggler. If you can reduce the gap down to 15 mm gap, the flux density higher for higher X-ray energy. This multiple wiggler design at 20 mm gap to produce 2.4 Tesla magnetic field. If you get 50 mm, the magnetic field higher, flux also higher for higher X-ray energy. This picture shows that the configuration of one unit of the magnet and pole. The blue color shows that the pole surrounded by the permanent magnet. The red block is the main magnet in the y direction. The green color is the side magnet located along the x-axis. This one unit is for one pole. Then we can model this kind of the structure in the code. This is an example of the size, dimension of the magnet and pole. Also material are shown in this table. Based on this parameter, we will make a model and simulation of the magnetic field in the Radia Python calculation. The Radia is developed in ESRF Accelerator Insertion Device Group, available from this website. There is a Mathematica version and Python version. Mathematica version Radia, Windows version only. However, Python is free. You can also download Radia ID package to calculate undulator and multiple wiggler magnetic field. The Python Radia displays the model in Windows by OpenGL function. However, the macOS version has no OpenGL, so we use VTK. This is the illustration of some model structure, periodic structure for even pole configuration and odd pole configuration, including the ending pole. So each unit and each period of the magnet precisely specify the magnetization direction, and if you want to make a chamfer design, you also have to be carefully design one by one. However, Radia has a function to mirror, so you have to make just half of the magnet can be model, and this model mirror the other side in x and y and z direction, so the calculation cost will be small. This slide shows that odd pole configuration. This point in the center of the wiggler, so the other side, the one side of the configuration can be modeled in this way. In the even pole configuration, the center of the wiggler located here, so slightly different configuration you have to make. If you need this chamfer or in Y direction or X direction, you have a two way to make this kind of structure. One is to cut the magnet model as shown in this slide, or you just specify Z point, the center of the rectangular position is the dimension of that rectangular. Next, you show the different Z direction, center of rectangular you specify, and the size of the rectangular also included. One after another, then you can make this polygon structure. Each dimension of the magnet and pole is specified in the code. In the original Radia ID Python code, based on the number of periods for only the odd number of the pole configuration. To make the even pole configuration, I revised the original code based on the number of pole. So you can, in this code, you can calculate 1, 2, 3, 4, 5, 6, 7, 8, 9 pole each configuration independently. Let's go to see the website, the ESRF Radia website. As shown here, you can download Radia for mathematical version only. If you go to GitHub, you can also download mathematical Python version. So you can download this package and extract it in your computer. This is another GitLab website from ESRF. You can download Radia ID and some utility to have a template code for undulator and multiple Wiggler hybrid calculation. Much easy to model. If you need some macOS version for Radia, you can also build each version of Radia. Then you can use the Radia on macOS. In case of BTK can be displayed from ParaView program. You can download also freely from this website. So after download, you will get this terminal command. Show these directories. We will go to Python directory, as you can see here. Depend on the Python version. In this case, I use 3.7. So you use this 3.7 version of SO file, copy to make a radia.so file from this file, and this delete it, and use this file for radia.so. Then you can run. Example file. For the other example, the plot geometry doesn't work in macOS. However, you can calculate field integral or field at center. You can see here. This is the field integral, vertical field, magnetic field, depend on the longitudinal position from example 3. Example 2. Example 3 is the hybrid planar undulator. The model doesn't show, as I said, however, the material, magnetic field hysteresis, and field strength versus the easy axis, field strength against perpendicular to easy axis, and this is the magnetic field, central field, depending on the longitudinal position. Let's see some of the code, Python code I wrote. For example, MPWPY is to calculate the undulator, as I show in the PowerPoint file. So we also import some detailed parameter from this file in the same directory with Radia. So you can specify the dimension of the magnet and pole, chamfer, and also subdivision and the magnetic material specified in this parameter part. And there is a code to produce to simulate the magnetic field in Radia, this kind of the multiple wiggle. Go back to MPW, and you can specify period. Actually, 2 pole is one period. The gap between the magnetic array upper and lower. The number of pole you can specify here instead of number of period to simulate the even and odd number of the pole. The material of the magnet. In case of neodymium iron boron, you can also specify the peak magnetization or minimum magnetization. If you have samarium cobalt, you can also specify. And this part is detailed the model parameter to calculate in Radia. And print wavelengths or the gap and peak magnetic field in the terminal. This code also saves the calculation. Later, if you wrote the save file, you don't have to recalculate the model. And you can plot the field or field integral, trajectory, and the magnetic force. This part export the geometry to BTK, so you can save the BTK file here, and using the ParaView, we can display the model. In the Windows version, you can use this plot geometry. However, macOS doesn't work here, so we export BTK file first and open again with ParaView program. So now we simply demonstrate the Radia calculation in case of number of pole 1. So as you can see, this is the field strength as a function of the distance of the magnetic array. The center field nearly 2 Tesla. However, the model doesn't show. Peak field strength actually display 2.38 Tesla. The total length of one pole is 300 millimeters. So actually this is the directory under Radia Python. And you show this VTK file produced after run the Python code. So this is the ParaView application. You can open VTK file. So this is already open here. Then you may apply the parameter without. So this is a model of one pole at the center and two ending pole. You can also show subdivision, the color you can change. And you can also change the display the subdivision. So you can see that subdivision. The number of subdivision is higher than the in the pole is higher to make an accurate calculation of the magnetic field, because this multiple wiggler produce the magnetic field mainly from this pole. So the subdivision of the pole number is higher than the magnet itself. The magnet actually produce the magnetic field to the pole. So the subdivision of the pole is not very high, not necessary to be higher. If the subdivision of the magnet or pole increase, the time spending to calculate the magnetic field also longer. Now we change the number of pole to be even number. For example, 2. Back to terminal. Run the command again. So this is the number of pole is 2 for the magnetic field calculation. The peak field strength is almost same as the that number that calculate in the one pole configuration. Let me display the model to check the two pole configuration. So you can see that the center of wiggler now come to the magnet, and the pole number of pole, as you can see, 2 of the pole is configured in between the ending magnet. If you want to show only pole, you change this build parameter to be pole. You can also change main magnet only, side magnet, and side and pole, main and pole, main and side. Full is the full set of the magnet and side and pole configuration you can display. Just for example, we try to display pole. So pole itself has no magnetic field, can be produced without magnet. Just to check the pole model, you can open this pole VTK file. Yes, this is the two pole configuration in between two ending pole. The ending pole is smaller to correct the electron orbit before and after the multipole wiggler or undulator. So the main X-ray produced from the main pole. The ending pole will work for electron beam correction. Now we go back to full magnetic pole and configuration. Number of pole to be 9, which is what we want to show in this kind of multiple wiggler. If you want to calculate number of point increase to plot the field along the y direction and also show x direction magnetic field strength distribution, you can also show the trajectory of the electron beam passing through this multiple wiggler. The field integral also display, but now we don't use it. So this code try to run. It takes some time longer because number of the point increase. However, result of the magnetic field is much smoother than the number of point is 100. Now is 1000 point I use to plot the magnetic field along the y direction. So the next figure shows magnetic field distribution in one y direction. So the beam passing through this small area. So depend on the magnetic side or pole size, you can control this flat range. Electron trajectory can be also displayed. In this case, electron coming from the left hand side and the electron slightly deviated after the magnetopole wiggler. This deviation should be corrected in the magnetic in the ending pole configuration. So finally, I would like to show this VTK for 9-pole configuration. As you can see that 9-pole in between the ending pole. You can also magnify detail to check your model is correct or is there any overlap between the magnet or side or pole and check the model is correct or not. You can see that.